Next bit is a group 1 chemistry. They want you to estimate the melting point of sodium. So what do you notice? This is down group 1. So down group 1, you see the melting point getting smaller and smaller. So melting point decrease. If I see the trend here is roughly decreased by, well, if I work on calculator, it's minus 24. It's going to be somewhere in between 63 and 101. If I was to make a guess, I would say probably like halfway in between would be like 100, somewhere like that, you know, just give or take. But essentially it has to be somewhere in between there. The next bit is atomic radius of rubidium. So you see how the size increase, the size of atom increase, because you have more filled electronic shells. So you have more shells that are filled. Here to here, you have a difference of around 0.034. Then the next bit, you have a difference of around 0.044. So if you increase further by roughly between this and this, it should be alright. So if I just take the middle value, you could take any of these. You can add 0.034 plus this, could be the answer. You can add this to this, could be the answer. I'm just going to add 0.04, which is somewhere in between, plus 0.235. This is just one possibility, and it's an estimate. No one knows the actual value unless you have data in front of you. Okay. Why it's difficult to predict the thermal conductivity of potassium? So have a look at the thermal conductivity. So here it continuously gets smaller. Here it continuously gets bigger. Here it increase. But from here to here, you see it decrease again. So it's very hard to predict that for potassium because of that, you know. While there is a specific trend, there are specific trends for melting point and atomic radius down group 1, but such a trend is missing, so it's not existent. So such a trend is not existent, or you could say absent, or you could say missing with thermal conductivity. So somewhere along the line that you don't see the trend, or you could just specify that from lithium to sodium it increased, but then it decreased again to rubidium. I mean, it's the same thing, there's no trend. Okay, I mean, the idea is there. Next bit, sodium plus oxygen give you Na2O. Be careful there, you got 2 sodium, so 2 sodium. You got 1 oxygen, but you got 2 there, so the only way to balance it is use a half. Half times 2 give you 1 oxygen. Okay, it's balanced. I know some teacher doesn't like the half, but even if you multiply the whole thing by 2, you will still get the same correct answer. The above will be acceptable. So sodium oxide is a basic oxide. I can write it out for you, or the best thing is I can show you what happened. So when you want to say it's a basic oxide, when you react that with water, what you're gonna get is NaOH. You're gonna balance the equation, and guess what? And it is a basic oxide because Na2O dissolve in water to give NaOH as the equation I show you above, which is alkaline. Basically, it dissociates in water. It dissociates in water to give you OH minus. Is also known as basic. That's it. Why copper doesn't react with sodium sulfate in terms of the ease of formation of ions? Explain in terms of the ease of formation of ions. So have a look on your data here. The ease of formation of ions. So they don't mention it here. Okay, let's think. Sodium sulfate is Na plus, 2 of it with SO4 2 minus, versus copper 2 plus, SO4 2 minus. So when you start from copper, you have to go to copper 2 plus. When you start from Na, you just go to Na plus. So there's the difference really. You only need to lose 1 electron. You need to lose 2 electrons for it to become copper 2 sulfate. So for sodium to form sodium sulfate, maybe I should just use formula. You should really know the correct formula. Na2SO4 only need to lose 1 electron to form Na plus. For copper, so copper solid, because you're writing copper, right, to form CuSO4, so that's copper 2 plus, need to lose 2 electrons to form copper 2 plus. Therefore, harder, more difficult. You need one more step. More difficult to react compared with sodium sulfate. Okay, I hope that makes sense. Now the next part, predict the names. So you need more than one. You need the products. When chromium reacts with dilute hydrochloric acid. The thing is, they already told you that something about chromium 3 there. So you should know that you have to use the oxidation number to indicate the product. So essentially what you have is metal plus acid, give you metal salt plus hydrogen gas, yeah? Okay, so there's a classic metal plus acid. So you're gonna get chromium. You're gonna get chromium 3. You are reacting with chloric acid, therefore you're gonna get chromium 3 chloride. And the other product will be hydrogen, because they actually want you to list more than one product, and the other product is just hydrogen when you react metal with acid. Next bit, ionic equation with stat symbols. So you will start off from chromium 3 plus aqueous. You will react that with powder zinc. So zinc is more reactive metal than chromium. So this will give you a zinc 2 plus, and then it will displace chromium out. The thing is, here you would need a solid, and you should probably put down there is aqueous, and then chromium, which is a metal and it's a solid. Your atoms are balanced, no problem. Your charge is not balanced, that is a problem. Okay, so this is 3 plus, this is 2 plus, and there are different atoms there, so you can't really, I suppose you can think about balancing the charge just from there, because there's no charge there. So you can think about the LCM of 3 and 2, and then it will give you LCM equal to lowest common multiple, 2 times 3 is 6. To go from 3 to 6 plus here, to go from 2 to 6 plus here, I need 3 times 2 plus, I need 2 times 3 plus. So the charge are balanced now. Now I have 2 chromium, I need 2 there. I have 3 zinc, I need 3 there. So I need 3 zinc there, and I need 2 chromium there. So that's it really. Explain why aluminium does not react with water. Okay, so aluminium is considered one of the reactive metal, right? But why does it not react with water? It's to do with due to a protective coating. So it's a protective coating around aluminium as a result of aluminium being oxidized in air. So aluminium being oxidized by the oxygen in air. Oxygen in air. This Al2O3 coating protects or prevents reaction with water. Okay, next bit. Hydrogen peroxide, an oxidizing agent, is added to Ki. So I minus is a very good reducing agent. And what you will get is this one is colorless, but it will form I2, which is aqueous in solution. This is not colorless. So you should know the color of aqueous iodine. So this is going to go from colorless to brown solution. Remember, this is not dark blue or black because you did not add starch. If there is no starch, there is no dark blue or dark black solution. This is aqueous iodine with no starch. It's just a light brown solution. So you gotta be careful. Just because you see iodine, it's not blue black. Are you having aqueous iodine, or are you having aqueous iodine in starch solution? Okay. So now chromium is extracted from chromium trioxide with aluminium. So your reactant is aluminium plus chromium trioxide. You're gonna extract chromium. And when you do that, the oxygen is going to go to aluminium. It's going to form Al2O3. So Al3 plus O2 minus. Case study, right? Electrolysis of Al2O3. Got to balance your equation. So you got 2 chromium. So 2 chromium. You got 2 aluminium. Therefore, you got 2 aluminium and 2 chromium. Every equation you write must be balanced in chemistry. Yeah. Okay. Either you get the formula wrong, or you are just not reading the question carefully. But most likely, if you gotten the formula wrong, you will have gotten the equation unbalanced, obviously. You want to suggest compound, reduce that to that. So, you want chromium 3 to go to chromium. So you want to displace chromium to form this chromium metal, right? So to do that, you need a more reactive metal compound that can displace chromium out of chromium compound. So you need a compound. So you're doing reduction here. Oh yeah, okay, I guess so. Yeah, I mean Ki. This is a very strong reducing agent. So what you can do is reducing agent can reduce this to chromium. I mean, potassium iodide is in front of you, right? Potassium iodide. Step 1 advantage of recycling metals, avoid landfill waste. So instead of it going to waste, you can avoid the landfill waste. Basically all that disposal of rubbish and stuff, and obviously extraction of metals. In this case, you don't need electrolysis, but where you need electrolysis, it's going to cost you a lot of energy as well. So that's why we recycle aluminium, because the extraction of aluminium is very energy intensive and costs a lot of money, obviously. What's meant by alloy? So alloy is a mixture. It's a mixture, obviously, so you still have the individual chemical properties. Yeah, okay, so you haven't changed anything yet. You just mixed 2 metals together. Yeah, 2 or more metals. You can have 2, you can have 3, you can have more actually. Okay, 2 or more metals. So make sure 2 or more metals with another element, maybe. So it can be, it's not just a mixture of metals, you can have it with another element, or more metals, or with another element. A mixture of, well, maybe I should rephrase that. Mixture of a metal with another element, which could be with another element, which could be a metal or non-metal. But what is important is it's a mixture. You are not reacting the 2 together. Okay, I think this is the last question in this paper.